In this video, I want to introduce you to second-order differential equations and take a look at one type of second-order differential equation that we can actually solve. So, what is a second-order differential equation? Well, it's an equation, first of all, and it's got a second derivative involved in it. So, ordinary second-order differential equation would look like this. Second derivative of y with respect to t can equal some function of t, y, and y prime, right? With our first order, we didn't have second derivatives involved. We just had those three things involved, but now we've got a second derivative in there as well. For as much fun as we had solving first order equations, second order equations are even more complicated. And there's really only a few that we can tackle here in an introductory class. So we're going to take a look at that type. I should point out before we do that initial conditions, if you had an initial value problem with first order differential equation, right, you'd have the equation and you'd have one point essentially that you wanted your path to go through. As it turns out, with second order differential equations, you have to give essentially two bits of information for your initial conditions, like a point that it goes through and the slope that you want at that point, or maybe 2 points that you want your curve to go through. Okay. Anyway, we will take a look at those as we go here. So the type of differential equation that we're going to be able to tackle here to start with is what's called a second order linear differential equation. And this is where I'm looking, comparing this equation here to what I have there. The function over here, if it is linear in y, and y prime, we would call this a linear second order equation. So you've got the second derivative of y with respect to t is equal to some function of t. This isn't necessarily linear. It could be any function of t. Minus p of t y prime, where p of t is, again, any function of t, minus q of ty, where q is, again, any function of t. So the linearity comes in the fact that the y prime, and the y double prime are all only to the first power. I write it this way just to make it look like the original, but usually when we're solving these things, we want to get everything, well, not everything, but get the y and its derivatives all over on the left-hand side here. So it would look more like this: y double prime plus p of t y prime plus q of t y equals g of t. Okay. We should point out that this is what I would generally look at and say, hey, yeah, that's second order linear. If the g of t is just 0, then we would call it second order homogeneous. It's a linear equation. That's a homogeneous equation because the constant over there, well, constant. The function over here on the right is the constant 0. Okay. And so, of course, that would look like this. Now, in general, these are actually still pretty hard to solve. And we are going to look at a more specific type, namely something that looks like this, where essentially the p and the q are just constants. This is called a second order homogeneous with constant coefficients. That's my shorthand here, SOHWCC, short second order homogeneous with constant coefficients, yes. Interestingly, when we write these homogeneous or linear equations, we typically do it in a way that has a 1 in front of the y double prime. If there's something other than a 1 right there, we would typically divide both sides of the equation by that in order to get a 1 right there. Whatever. And yet, when we do these second order homogeneous with constant coefficients, we quite often, at least in the general case, we put a coefficient in front of here too. Of course, you could just divide by it and have a 1 right there and have a b over a here and a c over a there. It's equivalent, okay, as long as a is not equal to 0. But if a was equal to 0, this wouldn't be second order and we wouldn't even be talking about it. Okay.